NASA's twin Voyager probes, which were launched in 1977, of the world with historic journeys to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their trip into interstellar space 45 years later. Researchers, some of whom are more recent than the spacecraft, are currently using the Voyager data to unravel mysteries within and beyond our solar system. In many ways, NASA's twin Voyager spacecraft have evolved into time capsules of their age. They contain around 3 million times less memory, and contemporary cell phones transmit data at a rate which is about 38.0 times slower than a 5G internet connection, and each one has an 8-track tape recorder for data storage. The Voyagers are still at the forefront of space exploration. In spite of this, what are they doing right now? What will the Voyager spacecraft encounter following that? Let's find out. Two of the most amazing spacecraft ever launched would never have taken flight if the stars hadn't lined up. In this instance, the 4 largest planets in our solar system were the stars. As a result of this coincidence, a spacecraft may gain speed from the gravitational pull of each large planet it passed, as if being pulled along by an invisible rope that suddenly broke, sending the probe flying on its course. One drawback, though the alignment only took place once every 176 years. A spaceship would need to be launched by the mid-1970s in order to reach the planets while the lineup was still in effect. As it turned out, NASA created two spacecraft to make the most of that once-in-a-lifetime chance. Within 15 days of one another, Voyager 1 and Voyager 2, which were identical in every way, were launched in the summer of 1977. They have been operating in space for almost 45 years and send data back to Earth every day from the solar system's farthest known planets. They have lasted longer than any other spacecraft in history and have traveled further. According to our best understanding of the dividing line between the Sun's sphere of influence and the rest of the galaxy, they have entered interstellar space. They are the first items created by humans to do so, and they will continue to hold this distinction for at least a few more decades. Overall, not a bad record given that the Voyager missions were initially only intended to last for years. The Voyager spacecraft's earlier observations of Jupiter's and Saturn's moons, which they provided to stunned researchers 40 years ago, revealed the presence of active volcanoes and fissure ice fields on worlds that astronomers had assumed would be as inactive and crater-pocked as our own moon. Voyager 2 was the first spacecraft to pass by Uranus in 1986, and 3 years later it flew by Neptune. It is the only spacecraft to have traveled in this way so far. They are currently surprising physicists with a number of unexpected discoveries about that unexplored region as pioneering interstellar probes more than 12 billion miles from Earth. Finally, their amazing voyage is coming to an end. NASA has turned off heaters and other non-essential components during the past 3 years in order to stretch the spacecraft's energy reserves as far as possible to an estimated 2030. It is a bittersweet moment for the scientists on board the Voyagers, many of whom have been involved with the expedition from the beginning. They are now faced with the completion of a project that is far beyond their highest hopes. 546 days after its launch, in March 1979, Voyager 1 arrived at Jupiter. Voyager 2, which had taken a different course, arrived in July of that same year. For its Vidicon cameras, which used red, green, and blue filters to create the full-color images, both spacecraft were built to be stable platforms. Since their rotating velocity is more than 15 times slower than the crawl of a clock's hand, they barely spin at all as they travel across space, reducing the likelihood of visual blur. The spacecraft began transmitting the first images of Jupiter despite still being around 3 to 4 months away from the planet, to the delights of standing-room-only crowds at JPL. It was absolutely unexpected when Io showed up in color. Prior to the Voyager missions, it was believed that all moons in the solar system would appear similar, drab and cratered. The incredible diversity of moonscapes the Voyagers found near Jupiter and Saturn was not predicted. The first indication that there might be more moon types than astronomers had imagined appear when the Voyagers were still 1 million miles or so away from Jupiter. One of their devices, the Low-Energy Charged Particle LECP detection system, detected some peculiar signals. Io had active volcanoes, as revealed by the cameras on board the Voyagers. The little world, which is slightly bigger than the Earth's moon, is now understood to be the solar system's most volcanically active body. The components ejected by the moon's volcanoes are what give Io its hues and the anomalous ions that strike Crimacus's detector. Teal, the greatest of Io's volcanoes, has produced plumes 30 times higher than Mount Everest, and its ash field is almost the size of France. The Voyager spacecraft captured more than 33,000 images of Jupiter and its satellites in total. Every photograph seemed to reveal something new. Jupiter had rings. Europa, one of Jupiter's 53 named moons, had an icy covering that was shattered and now thought to be more than 60 miles thick. The spacecraft received a farewell kick of 35,700 miles per hour as they were leaving the Jupiter system thanks to a gravity assist. Without it, they would not have been able to escape the Sun's gravitational pull and travel to another star. The Voyager split off at Saturn. Voyager 1 passed by Titan, the moon cloaked in orange smoke, and then turned north, away from the plane of the planets, after hurtling through Saturn's rings and taking hundreds of strikes from dust particles. Uranus and Neptune were the next stops for Voyager 2 alone. In 1986, Voyager 2 discovered 10 brand new moons orbiting Uranus, bringing the planet's ringed world counts to an ever-growing number. 3 years later, Voyager 2 observed the fastest wind speeds ever recorded for a planet in the solar system, up to 10 miles per hour as it passed around 2,980 miles above Neptune's azure methane atmosphere. Triton, the biggest moon of Neptune, was discovered to be one of the solar system's coldest locations, with a surface temperature of just -391 degrees Fahrenheit, that's -235 degrees Celsius. Nitrogen gas and powdered particles were ejected 5 miles into the moon's atmosphere by ice volcanoes. If Carl Sagan, an astronomer who was a member of the mission's imaging crew, hadn't been there, Voyager 2's pictures of Neptune and its moons would have been the last ones ever taken by either of the spacecraft. NASA intended to turn off the cameras on both spacecraft once the Grand Tour was formally over. There would have been no photo opportunities after Neptune, only the unending nothingness and impossibly far-off stars. Despite the facts that the project had been extended in the hopes that the Voyagers would reach interstellar space and had been renamed the Voyager Interstellar mission, Sagan pleaded with NASA leaders to order Voyager 1 to send one more batch of pictures. As a result, the probe pointed its cameras back toward the inner solar system on Valentine's Day in 1990 and snapped 60 final pictures. Earth was grabbed by the most mesmerizing of them all, known by Sagan as the pale blue dot. At a distance of 3.8 billion miles, it is still the furthest depiction of our planet ever captured. Earth is hardly discernible in the photograph, hidden by dim sunlight that was reflected off the camera's optics. It doesn't even take up a whole pixel. Both Voyagers are now so far from Earth that a one-way radio signal traveling at the speed of light takes almost 22 hours to reach Voyager 1 and just over 18 to catch up with Voyager 2. They advance by 3 to 4 light seconds every day. The NASA Deep Space Network, a trio of tracking facilities dispersed across the globe that allows for continual communication with spacecraft while Earth revolves, is their only connection to Earth. The Voyager signals are getting fainter and fainter as they move farther away from us in space and time. The world is really nosy. Everything produces noise: radios, televisions, cell phones, etc. Thus hearing these slight squeaks from the spaceship becomes increasingly difficult. Even though they are faint, those whispers have altered what astronomers anticipated the Voyagers would discover as they moved into the interstellar portion of their journey. You're advised to avoid confusing the solar system's limit with that of interstellar space. The Oort cloud, a far-off collection of comet-like entities held together by the gravity of the Sun, may extend halfway to the nearest star. It will take at least another 300 years for the Voyagers to arrive at its near edge. However, interstellar space is far more accessible. Where the solar wind phenomena ends is where it starts. The solar wind is a continuous outpouring of charged particles and magnetic fields that the Sun, like all stars, emits. Moving at hypersonic speeds, the wind blows out from the Sun like an inflating balloon, forming what astronomers call the heliosphere. The magnetic field of the Sun is carried into space together with the solar wind. The heliosphere's expansion is eventually restrained by interstellar matter pressure, forming a boundary with interstellar space that is preceded by a massive shock front known as termination shock. The heliopause is a border between our solar system and interstellar space, and estimates of its distance before the Voyager missions fluctuated significantly. According to Gurney, frankly, some of them were just assumptions. One early guesstimate located the heliopause as close as Jupiter. Gurney's calculations from 1993 put the distance at around 25 times further, between 116 and 177 astronomical units. 10, or 93 million miles, is the distance between the Earth and the Sun. Gurney's projections from 1993 were accurate. Before one of the Voyagers ultimately reached the heliopause, about 20 years had elapsed. Voyager 1 had actually detected the anticipated rise in plasma density. Its plasma wave detector at O inferred an 80-fold increase, but there had been no indication of a shift in the ambient magnetic field's direction. Shouldn't that change have been apparent if the vehicle had traveled from a place where the magnetic field originated from the Sun to one where it came from other stars? That was a shocker. In November 2018, Voyager 2 arrived at the interstellar seashore, but did not notice any magnetic field changes. When the spacecraft reached the heliopause at 120 astronomical units from Earth, the same distance reached by its twin 6 years earlier, it added still another riddle. All theoretical models predicted that the heliosphere should ebb and flow in time with the Sun's 11-year cycle, but this did not fit any of them. The solar wind ebbs and flows at that time. When Voyager 2 arrived, the solar wind was at its strongest, and if the predictions were accurate, the heliopause should have been further out than 120. Theorists' models of the interaction between the heliosphere and the interstellar environments are getting more intricate now that the Voyagers are providing them with some actual field data. According to the general image, our Sun left a hot ionized zone and entered a patchy, partially ionized section of the galaxy.